Hey everyone, welcome to our chemistry session, our chemistry CRAM session with Fiveable. Once again, I'm Wes. Good to see all of you. Hopefully everyone's doing swell on this lovely Thursday over in Santa Cruz. The weather is quite nice. I'm very, very happy. So last Tuesday, I started off our session by asking you what your least favorite or your most uncomfortable unit in the world of AP Chemistry was. Today, we're just gonna flip it and see what's been your favorite unit in chemistry. What's the coolest thing you've learned? What's the thing that you just didn't expect to really like, but actually really enjoyed? Um, Dakota says acids and bases. Um, Dang, that you might be one of the only people to say acids and bases. Mathematically, that unit is tough. But I actually really like acids and bases too, so I feel that. Periodic trends, I really enjoy the quantum stuff that like leads up into the periodic trends. I think that's a really excellent part of the unit. Let's see, for me, I actually really like the quantum history. All the stuff that leads up to determining electron configurations, quantum mechanics, like that is the coolest and most fascinating history, and also the math behind it is super cool too. Right, think about it, like scientists are trying to describe electrons using classical mechanics, and then they get about halfway through and they're like, oh boy, this math and science doesn't work. So, and then Magna says that thermochem is her favorite, so that's good. We are doing thermochemistry today, so I think on that note, why don't we go ahead and get started? Just a reminder for everybody. Down below, you have an Ask a Question tab. Down on the right hand side, you can write a comment or a question in the side there as well. And as always, I post my slides, which is the little green button right below where I am currently talking. So let's get into it. So we're going to do today thermochemistry, which is unit 6, the second to last unit on which you could be tested on. So that's kind of exciting. We have almost covered all the material that we are going to cover as a group here, which is also kind of rad, also kind of interesting, and yeah, geez Louise, exactly. We are almost there. So just a couple of upcoming things. First off, equilibrium is going to be what we cover next Tuesday. Our friend products over reactants, ice tables, stuff like that. It's going to be a whiteboard heavy session, I have a feeling. And then on May 7th, what I'm going to do is kind of compile some practice questions, give you a little kind of tricks and tips for the AP test, which will be the following week on the 14th. We as a group, as a company, are going to do a final CRAM on the day before the test on May 13th. And pretty much all afternoon, the chemistry crowdcast session will be open and available for you to hop on. I teach for some of the day, so I won't be able to be here for all of it, but I will be here for some of it. So I'll be here for at least the last 2 hours of that session. Thermodynamics. Okay, so I'm going to pause here and say thermodynamics is the name of this unit. Thermodynamics is the name of the unit, but it's only enthalpy. It's only, I should clarify, it's only going to be value delta H. Okay, so none of the delta G, none of the delta S stuff is going to be on the test. So applications of thermodynamics is not on the test. Delta H is on the test. Enthalpy is on the test. So that's something you should kind of be prepared for and make sure you're ready to understand, which is perfect, which is what we're going to be talking about today. So anything that I discuss or go over today that you're looking at and going, ooh, I don't remember it, luckily we have you covered, and we can maybe even do some of those questions in the AMA, which will be once again in a week from today. And so what I'm going to be doing is kind of formatting that practice session, kind of like an AP test, where I will ask you questions that are kind of all over the place. I'll maybe give you a chemical reaction and then ask you to draw a Lewis structure from something within the chemical reaction, do some stoichiometry. And yeah, it'll be all over the place. But just in case you can't make it, first off, I uploaded almost the night of, so you'll be able to kind of go in and check out the video sessions afterwards. And also, I model a lot of my questions after the practice questions. You should be looking at those at this point. Hopefully, your teachers are done covering new material. So really, we're just kind of in the review mode at this point in time. For any other information or stuff that you need, of course, Twitter, YouTube, Instagram, all those good stuff. So what are we gonna do today? Let me go ahead and paint a picture. Let me make sure you guys understand kind of how I like to envision this section. Okay, so first off, enthalpy is the name of the game. We want to make sure we're very comfortable with what enthalpy, the value H is, and how to use it. These are going to be coming from our thermochemical equations, where if I go ahead and have like a combustion reaction and I know the enthalpy value, and I say, okay, let's say I take 25 grams of this organic molecule and burn it, how much energy is released? Given all the appropriate quantitative values, you'll be able to answer that. And at this point, you should also know that pretty much any chemical reaction or process will either absorb or release energy. And so that's kind of what we're looking at here. The enthalpy is basically that value that tells us how much energy is released or absorbed by a chemical reaction or process. And then for the rest of our session today, what we're going to be looking at is how do we actually determine that enthalpy value? We can look at calorimetry. Calorimetry is the experimentation where we go ahead and do a chemical reaction and measure the temperature change. We can use Hess's law, which is our ability to kind of take the fact that enthalpy is a state function. We can use heats of formation and bond energies. There's so many different ways for us to actually calculate what enthalpy is that it gets literally its whole unit. So without further ado, let me go ahead and get started. Once again, I want to remind everyone that you can ask questions over on the side or down below in the Ask a Question section. I will get to them. I might not get to it immediately, but I'll kind of take pausing points throughout my session today to make sure to answer your questions that I'm sure a lot of you guys have. So without further ado, let's jump into it. I always like to start off my sessions in thermochemistry and thermodynamics with making sure we understand some of the very important vocabulary. So energy is specifically the ability to do work or transfer heat and transfer heat. Work is defined as a force, acting over a distance. Pretty much what I want to say about work is this. Since applications, Unit 9, applications of thermodynamics, isn't going to be on the test, work is no longer as important of a vocabulary word, but it's still important enough because the units are joules. It's a function of energy. So making sure you kind of understand it on a fairly qualitative level, you'll be good. Heat is the important one for this unit. Heat is going to be the transfer of energy from something hot to something cold. And the way we kind of quantify and look at something that is hot or cold is those particle motions, right? Particles that are moving really quickly and bouncing off of each other and colliding with their neighbors are going to have a high temperature. And when something that is hot, something that is particles that are moving really quickly, come into contact that is something that is cold, the particles are moving very slowly. The particles' energy gets transferred from the hot particles to the cold ones, causing the cold particles to move faster and the hot particles to move slower. So the reason and the thing that you should be thinking about is that whenever there's an energy change from hot to cold, it has to do with the particles colliding and the particles quite literally transferring their kinetic energy. Temperature is, once again, and this is like the 5th time I've brought this up, temperature is the measure of the average kinetic energy. You need to remember that one. They'll probably ask you to define it without specifically saying define temperature. The last couple vocab words that I want to go over is kinetic and potential energy. So kinetic energy, as we know, is the energy due to motion and is dependent on the mass and velocity of the particles. So generally speaking, if we kind of go back to our gas unit, gas particles that have a heavy mass tend to move slower. Particles with a lighter mass tend to move faster. And at the end of the day, particles that have a high or large kinetic energy are going to be measured to be hotter. And the other important one that's kind of been gleaned over or maybe discussed but not defined up to this point is potential energy. And there's definitely a physics heavy definition and a chemistry heavy definition, this being chemistry. Yeah, chemistry. We're going to look at the chemistry heavy definition. Basically, when we're looking at potential energy in the world of chemistry, we're looking at how particles interact with other particles, and the big attractive or repulsive force that is felt between two particles is going to be due to charge differences or charge similarities. Essentially, when we're looking at potential energy, we're referring to the energy due to composition or makeup. We looked at intermolecular forces and there being forces of attraction between dipoles of polar molecules. And we've even looked at chemical bonds where after an electron is transferred between two ions, between a metal and a nonmetal, one becomes positively charged and the other becomes negatively charged. And that force of attraction brings them together. So there is definitely going to be a lot of energy stored in chemical bonds. Last but not least, and I think this is kind of something that I really want to drive home today, is that the system is the thing that we're studying, the surrounding is everything else. And at the end of the day, energy transfer, heat transfer, will always be between the system and the surrounding. And your ability to kind of separate those two things and understand, hey, is energy going in or out, will really help you understand some of these processes that are happening. There's a lot of kind of funky, what's the word I'm looking for? Not implications, assumptions and things that we have to consider when we're doing enthalpy and energy. And one of those things is that we can only specifically study energy changes. This has to do with a lot of the definitions that I'm foregoing, but you can only ever study the final and initial state, but not just one of those by themselves. So where is energy going? It's either going from the system to the surrounding or from the surrounding to the system. And in chemistry, the system is always the chemical reactions. So that's one thing that I really want you to kind of keep on the back of your mind, okay? So here you go for your viewing pleasure. It's a temperature-related joke. Popcorn. Okay, great. Enthalpy. Here we go. So the specific enthalpy value has a definition. It is the measure of the internal energy plus the pressure volume work plus pressure times volume. You will not be asked that. You will not have to regurgitate that. What is important is this. The change in enthalpy is quantitatively equal to the heat released or absorbed by a reaction at a constant pressure. So essentially, the value of delta H is equal to Q under very specific circumstances, and that specific circumstance is pressure. Because we chemists are doing pressure on planet Earth, the pressure stays constant. It's always going to be 1 atmosphere of pressure. And so therefore, yeah, we can pretty much make the assumption that enthalpy, the change in enthalpy is quantitatively equal to heat. Now, what's super fun, and like I got my degree in chemistry. I took a thermodynamics class when I went to college, and basically like they teach you how manipulating pressure and volume actually affects this quantitative value called enthalpy, and then you cry a lot, and it's a great time. College is great. It's basically 4 years of crying and losing a lot of money, but at the same time, it's also super fun, and I did learn a lot. We'll go back to college on another time. So as far as this goes, I think that students always have trouble understanding that there actually is a difference between heat and enthalpy. There totally is a difference. And I really like to try my best to make sure you understand this as we go through. So when we are looking at heat, heat is the actual value. What I mean by that is heat is synonymous to mass, meaning that like I can have a big pile of stuff and the mass would be heavier, or I can have a small pile of stuff and the mass would be lighter. I could release a lot of energy and the heat absorbed or released would be greater. The heat, if I let a little bit of energy out, the heat released would be smaller. Enthalpy is always the same. So if I'm comparing heat to mass, enthalpy is very similar to molar mass. Molar mass for a chemical cannot change. The enthalpy for a chemical reaction or process cannot change. Now, I can manipulate that, but by manipulating it, I'm also changing the coefficients or direction of the chemical reaction. So the very specific chemical reaction that I'm studying isn't identical to that. So enthalpy is always for a very specific chemical reaction. Heat is the amount of energy that is transferred in a specific reaction, while enthalpy is the conversion factor that relates heat to moles of reactant or product, and we use it just like the mole ratio. So here's our first reaction. This is the combustion of methane. We have the balanced reaction here, and the units for enthalpy are often going to be kilojoules per mole of reaction. Basically, one way we can kind of look at it is for every mole of CH4 that reacts with 2 moles of O2, I'm going to release 890 kilojoules of energy. I could also say something along the lines of for every 1 mole of carbon dioxide that's produced, 2 moles of water are also produced, and 890 kilojoules of energy are released in that reaction. So essentially what this is going to say is that if we were to double any of these values or halve any of these values, the enthalpy value would also be doubled or halved respectively. Enthalpy acts as a conversion factor. Enthalpy acts as a conversion factor. Oh yeah, it acts as a conversion factor. One of the things that I want you to understand about this is that you can rewrite this, and sometimes when I was learning this, I found that writing thermochemical equations really helped me understand this process a little bit better. So if I were to take the chemical reaction that I had before, which is this, CH4 plus 2O2 yields CO2 and 2H2O, the delta H value is negative 890 kilojoules of energy. If I were to rewrite it, I could literally add the heat energy as a product. Now, energy isn't a product. Remember, product has to be some sort of matter, but it gets the job done, especially when we approach some of the mathematics. The combustion of ethane and really the combustion of any substance is going to be an exothermic reaction. And exothermic reactions are when we transfer energy from the system to the surrounding. So energy leaves the system. Generally speaking, exothermic reactions will make the surrounding hotter. And endothermic reactions are going to be when we absorb energy from the surrounding into the system. And generally speaking, the endothermic reactions will make the surrounding cooler. You as a human, you as a student, you as a chemistry person are always the surrounding. So one of the things you can kind of think about is hey, how does that feel to me? And that will usually get the job done. But be careful with this because you really want to make sure you understand where did I start and where did I end. That's going to be the bigger defining piece for this, okay? So let's kind of continue on. Here's an example, the formation of nitrogen monoxide or nitrous oxide from its constituent elements. This is an endothermic reaction, and it's endothermic because, and you should be very comfortable with this, it's endothermic because the delta H value is positive. So if I wanted to rewrite it as a thermochemical equation, I would write it on the left-hand side as if it were a reactant, A couple of last little things here. When we're looking at energy values, I want to make sure you guys understand that there is no such thing as a negative energy. There's no such thing as a negative energy. And then immediately all of you guys are like, wait a minute, there's like 30 negatives that you have written all over your slides. And that's because it tells us something. Whenever you see a negative energy, it's just telling you that in the process that we're studying, in the reaction we're studying, energy is leaving the system and going into the surrounding. Now, something that's fairly new and came up more specifically in this unit is moles of reaction. And I don't want you to get overwhelmed or freak out when you see that. It's actually quite easy to approach. The mole of reaction is an arbitrary value, which essentially relates the moles of the balanced reaction to the enthalpy. When we're looking at this, we want to look at the coefficients. So for example, we know the coefficient in front of N2 is 1, O2 is 1, and NO is 2, respectively. So we can set up our mole ratio in the following way. It's a 1 to 1 to 2 ratio. However, the coefficient for mole of reaction will always be 1. And you can equate that to other chemicals in your balanced chemical reactions by putting the coefficient of that chemical in front of in front of whatever you're going to be using. So once again, mole of reaction is fairly new. I think it was something that was introduced in the 2014 revamp of the chemistry test, but it's nothing you should be kind of overwhelmed or freaked out about. When you see mole of reaction, just realize that it's one of the ways they're trying to help us realize that you can convert between the moles of reactants or products to the enthalpy. And let's see how they can do that. So here's our first question of today. I've been having a little bit of issue with my Wi-Fi, so I'll jump to the whiteboard at the end of our session today. But let's go and check it out. And I wrote the solutions up so you can see them in a second. What amount of energy is needed in order to produce 75 grams of NO? Now, notice some of the language I used when I wrote this question. I said amount of energy is needed. I've already described that, hey, because the delta H value for the formation of NO is endothermic, it's positive, it's endothermic. So I need this energy in order to make it. It's going to come from the surrounding, and it'll probably feel cool to us if we were around when this reaction occurred. So what I'm going to do is this. I'm going to take the 75 grams of NO, convert it to moles of NO. And I do that by using the molar mass of NO. Look at that. Once I do that, I see the coefficient in front of NO is 2, and I can relate that to the enthalpy of the reaction. So essentially, the math is going to end up looking like this, where 75 is going to be divided by the molar mass, once again, to get that value converted to moles. And then I know that for every 2 moles of NO that are produced in the chemical reaction, 181 kilojoules of energy is released. Do all the math, you go ahead and get a heat value of 226. Now, I just want to show you really quickly how I could use the new approach. Both of these ways work perfectly fine and are perfectly understood by the graders of the test. 75 grams of NO, you convert to moles. We know that for every 2 moles of NO, you're going to have 1 mole of reaction. And the delta H value provided to us says that for every 181 kilojoules of energy that are required, it will react with 1 mole of reaction. So it's, once again, it's not really a new thing. For stoichiometry or dimensional analysis, as you can see, it's a little pointless, just like barely like a tiny bit pointless. It will help us a little bit later on down the road when we're trying to determine enthalpy values for chemical reactions. So I'm going to pause here, field any questions that you may have about enthalpy, because at the end of the day, once again, you want to be able to use the enthalpy value pretty much in this way. Whenever you get a question that says how much energy is released or produced, you either need to use a dimensional analysis with the enthalpy value or the next thing, which I'm going to show you in a second. Probably, you asked an interesting question in regards to Le Chatelier's principle. I think if you said something along the lines of, if you think of heat as a product for like exothermic reactions, that kind of clarifies some of the some of the things that in language that is important within the world of chemistry. So yeah. For sure. Yeah. So, and then actually, that's a really good point, Perla. So, I said at the beginning of my session today that enthalpy and a lot of our thermodynamic values are dependent on pressure. And technically speaking, if you were to do some chemistry like in Colorado or I don't know, Nepal, somewhere with a really high elevation, your values would not match up perfectly. But the the atmospheric pressure is close enough that once again we can kind of make these assumptions. And you have to remember that we have a lot of standard values. So one of the standard values that we use, I don't know if you've ever noticed this, but when we do delta H, we often throw a little circle in the upper right-hand corner. And that basically tells us that we are studying this reaction under standard conditions, which is not the same thing as standard temperature and pressure. Yay. Standard conditions are going to be 20 degrees Celsius and 1 atmosphere pressure. So the standard pressure is the same. Stuff like that. All right, cool. All right, so let's go ahead and move on. And I'm going to I get to tell my favorite fact ever. And if any of you are my actual students, no spoiling. So specific heat, here we go. Specific heat is the amount of energy required to raise the temperature of 1 gram of substance by 1 degree Celsius. If you can remember water specific heat, write it in chat right now. I know some of you guys already know it. The big equation that is going to come up that a lot of you are probably very familiar with is Q equals mCp delta T. Some of you probably also just use Q equals mc delta T, and that works perfectly fine. Cp is technically for specific heat, and I'll explain why this is in just a second. Yeah, water specific heat is 4.184. Or just 4.18 joules per gram degree Celsius. And that basically tells us that it takes 4.18 joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius. This is a really large specific heat. And I always like to kind of say like, wow, that is super impressive. And this actually relates to my favorite chemistry fact, yes, chemistry fact ever. So we have Alaska on the board because it's one of two of the 50 United States that have never reached temperatures above 100 degrees Celsius. Does anyone happen to know what the other state is that hasn't reached temperatures above 100 degrees Fahrenheit? I said Celsius. My goodness, it's definitely never been above 100 degrees. It's never been above 100 degrees Celsius. That's really hot. And yes, you are correct. It's Hawaii. What the heck, right? Wait, really? Yes, really. So here's the thing. The highest recorded temperature, I know, seriously, right? That's such a mind-blowing fact. The highest recorded temperature for Hawaii is 99 to 100, depending on which articles you read. And the reason this is because water specific heat is so high. So even though it's way further south, it's closer to the equator, and getting way more sunlight than we currently are, all of that energy is going into the ocean that's surrounding Hawaii. I know for me, I live really close to the coast. Most of the time, coastal temperatures are significantly lower, and that's because there's a lot of water there. As I move more inland, so I go from like Santa Cruz, there's a city a little bit southeast of where I'm at called Watsonville. It gets warmer. And then, yeah, basically as you move further east or further west, depending on which coast you're at, it gets warmer. And that's because the land is made up of metal or rocks, which have lower specific heat, and it's easier to heat them up. So this is the equation you need to know. You should definitely have it on the back of your mind. It's definitely provided to you on the cheat sheet, on the formula sheet. Gayatri, that is awesome. And did you know that fact about Hawaii? So one of our viewers right now is like, I am in Hawaii. I live in Hawaii. I didn't. There you go. You should go tell all your chemistry students when you go back. All right. So moving on. One of the things that we can go ahead and study using and understanding specific heat is calorimetry. So there's actually two types of calorimetry I'm going to go over today. The first one is coffee cup calorimetry. And in the bottom right, I included the sign of my favorite coffee shop in Berkeley. It's called Brewed Awakening. Can't go wrong with a name like that. But coffee cup calorimetry is this. So it's synonymous with constant pressure calorimetry. And once again, what's the pressure that's going to be like measuring? What's the pressure, that we're going to be doing our chemistry in? It's going to be atmospheric pressure. It's the pressure that's surrounding us. So we can quite literally do experiments in a styrofoam cup, which I'm sure a lot of you did at school. Essentially, coffee cup calorimetry is going to be studying or observing aqueous reactions or dissolutions. So those aqueous reactions, we can study energy change between acid and base reactions. We can study temperature change for precipitation reactions. And we can also study temperature change and energy change when we dissolve salts into water. The purpose of the calorimetry reaction, the purpose of any calorimetry process, is to determine the enthalpy. Now, enthalpy can and is often measured in units of kilojoules per mole, but sometimes it's in kilojoules per gram. So this is where your reading skills are going to be super important. Make sure you're paying attention to, say, like what it says it wants the units in. If the units are in kilojoules per gram, then you can just use the molar mass or mass of the substance that you have. If it's wanting it in kilojoules per mole, make sure you make that conversion and have the mole values. The two equations that I'm going to provide for you are definitely unofficial equations, but they're really good equations for you to have on the back of your mind. In order to calculate the value of enthalpy, delta H, you either have to divide the heat that's released or absorbed by the process by the moles, or by the mass of whatever things are being reacted, dissolved, produced. Sometimes if you want to determine the amount of energy that's released for every mole of precipitate that's produced, that sometimes could come up. But the language for these is really important. And sometimes, it can be a little frustrating. So for example, one of the experiments that I do with my students is we burn marshmallows under an aluminum can, and then we compare how much energy was absorbed by the water in the aluminum can to the actual bag value. So when you're looking at calories on the side of food, it's quite literally telling you how much energy is released or stored in that food that we can kind of intake. One of the fun connections that I like to make in terms of combustion reactions is quite literally the reason we're alive is because of miniature combustion reactions happening inside of us. Not true, by the way. That's just a connection. It's kind of like that. Otherwise, we'd explode, which I don't want to explode. All right, so once again, by measuring the temperature change of the water in the aluminum can, we can actually determine how much energy was released when the marshmallow burned. So basically, by burning the marshmallow under the aluminum can, the water in the aluminum can is going to get hotter. And by using the Q equals MC delta T equation, I can actually observe the temperature change. I know the specific heat of water, and I know how heavy the water is, so I can determine how much energy, heat, was absorbed by the water. By connection, I say, hey, the water that was, the heat, energy that was absorbed by the water must have been released by the burning marshmallow. And by understanding how much marshmallow was burned, by taking the mass before and after it being burned, I can actually determine the energy content, or rather enthalpy, that's stored in the marshmallow. Now, chemistry, College Board, there we go, loves error analysis questions. And for this, hopefully you can already see what the question is going to be. Why would the energy value be higher or lower than what you should actually calculate? And one of the biggest source of errors is that the energy just went into the surrounding. It went into the air. If I'm doing this in an aluminum can, Some of that energy even went into heating up the aluminum can, and my thermometer unfortunately doesn't measure the temperature of the aluminum can. It only measures the temperature of the water. So sources of error are very specific and never, oh my gosh, never, ever, ever answer because it's of human error. Have a real reason. Think about the process. Think about what you did in the experiment or lab, and try to make a connection. It could be as easy as I spilled some of the chemical, which is human error, of course, but you can't just say human error. So let's go ahead and look at the last type of calorimeter, which is a bomb calorimeter. As far as bomb calorimetry goes, bomb calorimetry is going to be synonymous with constant volume calorimetry. So basically, we do chemical reactions in a rigid container, which the connection to bombs is just that most bombs occur in rigid containers, and you create a gas inside the rigid container until the pressure can no longer be held, and then it explodes out. So that's the connection here. We're not actually exploding anything in bomb calorimetry. Well, I'll let you decide on that one in a second. So these require very specific and technical devices that have heat capacities. The technical device is called a bomb calorimeter. The equation that is, once again, unofficial, but something you should absolutely have on the back of your mind, or cheat sheet or whatever, is CV is equal to Q divided by delta T. CV is very similar. CV is very similar to CP. CV is the heat capacity. If we go back to specific heat is referring to the amount of energy required to raise the temperature of 1 gram of substance by 1 degree Celsius. Heat capacity is telling us how much energy it takes to raise the temperature of the device, the bomb calorimeter, by 1 degree Celsius. So the only difference between CV and CP is that CV doesn't take into consideration the mass of the device you're using, whereas CP takes into consideration the actual chemical of the substance that you're actually using. Bomb calorimeters often are going to measure combustion reactions, and these are going to be used in like food calorimetry. So food chemistry, excuse me. So the device we had back here is a very, very crappy bomb calorimeter. When we actually have bomb calorimeters, they are completely sealed off to the atmosphere, and we actually measure the amount of heat that's absorbed, or excuse me, the temperature change of the actual bomb calorimeter. Okay, so basically what we've just discussed is we have enthalpy. Remember, enthalpy is going to determine and help us understand how to relate the amount of heat that's released by a chemical reaction and the amount of moles or mass of the reactants or products that are being reacted or being produced. We then moved on to calorimetry, and calorimetry is one of the many ways that it can actually help us determine the value of delta H. The unofficial equation that I gave you are listed down below here. Delta H is equal to the heat divided by the moles. It can also sometimes be asked to do it by mass. Just be very cognizant of the things you are reading. The next thing we're going to move on to, which I saw some of you said was your favorite, and that kind of makes me happy. It means that you guys are kind of puzzly like me, is Hess's law. And before we do that, I want to make sure that everyone's comfortable with how we can manipulate chemical reactions. So there are two very specific and important ways that we can actually manipulate or change these reactions. Way number one is flipping the reaction. So due to the law of conservation of energy, basically anytime I have a specific process, the amount of energy that's released or required would be exactly the same if I were to flip the direction of that reaction or process. By flipping the order of the reaction, so basically if I said I take the reactants and I'm turning them into the products, and now I turn it around and the products are returning into the reactants, the magnitude, the number of delta H stays the same, however the sign flips. So here's our lovely chemical combustion of of methane, excuse me. And if I were to flip the chemical reaction, we know that the value of delta H just becomes positive. Now, what I do want to say is this: not all of these chemical reactions are possible. For example, it is not possible to take carbon dioxide and water and re-smash them together to get methane and oxygen gas. But because of the fact that enthalpy is a state function, the math and energy values would work out in the exact same way. The other way that I can manipulate it is by multiplying by a coefficient. So if I multiply a reaction by a coefficient, I literally take the number that I multiplied and multiply the delta H value by the same number. You will not have to explain the concepts behind manipulations. You will just have to describe the manipulation that occurs. So here's my combustion of methane. If I go ahead and take the coefficient and multiply the entire reaction by 3, then the value of delta H, it looks like I multiplied it by 6. So 890 times 3 is not that number. Yeah, I multiplied it by 6. So I can go ahead and change that really quick. But by changing or taking the value, there we go, and multiplying it by a certain coefficient, then that coefficient is multiplied by the value of enthalpy as well. We will make it through one of my CRAM sessions where I don't have to change one number, I promise you. But today is not that day. Today is not that day. All right, cool. So what's the purpose of all these manipulations? Why do we have this ability, or what's kind of actually cool about this? Well, here's the thing. Hess's law is this ability or opportunity for us to determine the value of delta H for almost any chemical reaction as long as I know the enthalpies of some other chemical reactions. And that's so cool because we as chemists study literally millions of reactions, and I don't always have the ability to do like calorimetry, whether it be bomb or coffee cup calorimetry. And sometimes I just need to know how much energy would be released by a certain process on pen and paper. And that's what Hess's law kind of allows or affords for us to do. Hess's law utilizes the fact that enthalpy is a state function. And remember, a state function refers to a property that does not depend on the pathway. It only depends on the initial and final states of the system. If any of you guys took physics, one of the easiest explanations or examples of a state function that I like to give is displacement versus distance, right? If I were to travel up a mountain and go left, right, up, the displacement would literally just be the distance between the place that I started and the place that I ended, whereas the distance I traveled would be a lot longer. So as far as this goes, heat is not a state function because heat is released and then absorbed and then released every time I go through a chemical reaction, but enthalpy is. And what essentially this allows for us to do is that we can manipulate chemical reactions, and then notice how I said add the reactions, in order to determine the delta H value for some other different reaction. A lot of you guys, once again, are very comfortable with this, and some of you may not be stating that you are comfortable. I'm going to quickly walk through an example, and then if you haven't noticed or known this, we've been posting some questions in the community section of Fiveable. Kudos to Perla, who's pretty much been the only person who's answered those questions. But if you respond to one of those questions, I or somebody else in the community can respond to you there. So I'll make sure to upload a Hess's Law problem so you can check out what you're missing. This graph was talked about in our last session as well. I highly doubt you'll be asked to draw anything like this. This process or this graph is really just helping us represent the energetic values. Notice it's a one-directional graph, one-dimensional, I should say, graph, where we plot the relative energies of each one of the reactants or products. So let's look at the one-step reaction on the right-hand side first. If I were to take nitrogen and oxygen and combine them into NO2, the energy that's absorbed by that reaction would be 68 kilojoules of energy. I could also do this process in 2 steps. I could take the nitrogen and oxygen gas and first use it to make nitrogen monoxide, and then take the nitrogen monoxide and then react it with the oxygen gas to create the 2 NO2 molecules. Notice that it first goes significantly higher, and then the second reaction is exothermic, so it drops it back down. And notice that the difference between the starting point and the end point is exactly the same, and that's super important and useful for us to understand because enthalpy is a state function. By knowing the following reactions and their enthalpies, we can actually determine the enthalpy of the synthesis of NO2 from its constituent elements. Imagine if we didn't even know the process or the graph on the right-hand side. Imagine we didn't even do that reaction that's listed on the right-hand side. We could easily determine the value, the enthalpy value to be positive 68 if we knew the first 2 chemical reactions on the left and their enthalpy values. And then that's an extremely useful and important thing for us to do. Now, I'm almost finished here. I've got a couple more things that I want to clarify and point out. So this will be a great time to kind of field a couple more questions. Magna asks, I think, a really good question that is a fair question. So the question is this: what is the likelihood of us being asked to set up an experiment on the AP exam? And I think that the likelihood of them actually asking you to describe the processes and steps in the AP exam would be not high, but also not low. I would say somewhere in the lower to mid region of possibility. The reason that I say that is mostly because they're hard to grade, and there's so many specific and nitpicky types of questions that they ask on the AP test, that asking for an entire setup is a lot of work. Now, what they do ask, and this does come up often, is why did an experiment work better or worse than it should have, and making sure that you can actually approach that is good to understand. And they also love asking you about specific types of glassware, specific experimental devices. So they'll ask you to maybe like string a sentence or two together to describe like, hey, why did we use the volumetric pipette versus the graduated cylinder? And you're like, because the graduated pipette is more specific, you know, stuff like that. And yeah, you're totally right. They did ask an experimental setup question last year, but once again, they literally just wanted you to pick the specific pieces of glassware that were super important for that. So once again, that's why I said it's not impossible. They could totally ask you on it, but I would say it's like in the lower to mid likelihood. And then Trevor asked what would we use Hess's law for? And pretty much it's that. Like the whole session for us today has been, how do I want to say this? Our whole session today has been the first half, how can we use enthalpy? And the second half has been, how can we find enthalpy? One of the ways that we can find the enthalpy of a chemical reaction is through Hess's law. And so, yeah, literally the only purpose of Hess's law is to determine the value of delta H for another chemical reaction. And then once we know that, we can then go back to the first half of our session and actually use it. I heard a rumor that there's a limit to the amount of pages that you can submit. I heard, okay, so I read this today, and I need to do a little bit of research, like literally 10 minutes before I started streaming. That they are not accepting PDFs. We need to clarify that and talk about that with everybody. But from what I understand, they are not taking PDFs. So the second you said if you make a PDF, you can't do that. You can only upload JPEGs or HEIC files. I think HEIC files will work. But I hate reading those from my point of view as a teacher. But JPEGs and PDFs are way better. But yeah, no, I read that today. but I will clarify. And next week when I go over like test specific things, that will be one of the things I talk about. Yeah. So just pretty much taking a picture with your phone is what you're going to want to do. All right, let's go ahead and finish this off, guys. So the last couple of things that are super important are basically applications of Hess's law. The first application of Hess's law you've probably done like a bajillion times in your own respective chemistry classes, and that's using enthalpy or heat of formation. Heat of formation has a really specific definition, which always throws students off, which is kind of funny to me because I don't think it's that difficult of a vocab word, but I can appreciate something being difficult. So I feel your pain. Once again, enthalpy of formation refers to the amount of energy required to make 1 mole of something from its constituent elements. These are very, very well-studied values, and they are listed in the appendices in the back of your textbooks. For the AP test, they will literally give it to you. So if you see heat of formation, you want to like immediately throw this equation on your sheet because you will 99% of the time have to use it. We use the heats of formation to determine the enthalpy of a chemical reaction with this formula. Now, one of the other things that they ask, and is common, is they will actually ask you to determine the heat of formation, the enthalpy of formation, given other enthalpy of formations and the heat or enthalpy of a chemical reaction. So basically, like, you don't always just throw these values together to get the solution on the left-hand side of the equation. Sometimes you have to either solve for the heat of formation of the product or the heat of formation of the reactants, which is really just algebra. You absolutely are expected to know that the heat of formation of an element is 0, and that hopefully makes sense as well, because the constituent elements of an element is the element, right? So there was no process that occurred. So if you're like, hey, I'm missing the delta H for this thing, and they didn't tell me what it was, it's probably 0 because it's probably an element. All right, a couple more things. Bond energy. We can absolutely use the concept of bond energy in conjunction with Hess's law to determine, once again, the delta H of a reaction. You should know at this point, because I talked about it last week, that energy goes into breaking chemical bonds, and then energy is released when new bonds form. So essentially, if I'm looking at the chemicals on the left-hand side, what I'm going to do is add energy into breaking 1, 2 hydrogen single bonds. Energy goes into breaking a oxygen-oxygen double bond. And then energy is released when 4 oxygen-hydrogen bonds are formed. The chemical formula is a little backwards. Notice, look at what I just propagated on the screen. It says reactants minus products. This is only, okay, you listening? This is only for bond energies. Make sure you have that on the back of your mind when you are looking at this. It's pretty much always products minus reactants unless you're looking at bond energy values. So once again, the bond energy for H2 is 436. Bond energy for O2 is 495. And the bond energy for the OH bond is 463. So the math should look something like this, where I go and put energy into breaking the old reactant bonds. So that's the positive, that's the starting point. And I subtract the 4 bonds that are formed on the right-hand side. Adding up all the math, I go ahead and get that the chemical reaction that's represented by above is going to be roughly negative 485 kilojoules per mole. Happer and burp. I kind of like that. Yeah, that works. If you look in the comment section, it's a little kind of mnemonic that will help you. Or once again, just make sure you have these equations really close at hand and you can use those. All right, and what we're going to end with is this. This is what I actually really love about this section, is that it's sometimes a little overwhelming because it feels like you're learning so many different types of enthalpy values, and you are. And notice the title, heat of insert thing that happens here. And that's because we can study so many different types of enthalpy, right? Every chemical reaction and process absorbs and releases energy. So I can go ahead and look at the heat of combustion. And this refers to the energy released. It's a combustion reaction, so we're releasing energy when 1 mole of an organic molecule combusts. We could talk about the heat of vaporization or the heat of fusion, which refers to phase changes, right? If I were to go ahead and melt 1 mole of substance, I would have to use the heat of fusion. If I were to go ahead and evaporate 1 mole of substance, I would use the heat of vaporization. I can even measure the heat of dissolution, right? Which is referring to dissolving salts into water. In that situation, it may be endo or exothermic. Making sure that you know which things are exo and endothermic are going to be super important. Now, once again, Aparna, and anyone else who's looking at this going, holy crap, that's a lot of things, don't. What I'm trying to say is this. There's a trend to all the definitions that I wrote up here. All of them refer to how much energy was released or absorbed, and it's always referring to 1 mole of the substance being in that process. So if you see heat of combustion, you're like, okay, well, this is going to be a combustion reaction. You see heat of dissolution, oh, we're talking about something being dissolved. If we see heat of reaction, we know it's just a chemical reaction. You can describe many reactions with the heat that's absorbed or released by them. So yeah, the reason I'm ending with this is to once again make that connection for you guys that all these definitions are almost identical. The only thing that's different is what process we're studying the energy for. And that's it today, guys. So once again, I do want to go ahead and say, that on the community section in Fiveable, there have been some questions that I've been posting. Some of you have already answered some of them. And I just want to point out that if you want to try it out, don't look at the answers. Some of them are right. And yeah, you can look at older ones. They're all still available for you to check out and work on. And yeah. So what you're going to do, let me see if I can show you from my view. Let's do this. Cool. All right, cool. So you can actually see from my point of view. First off, look at how many extra things I have. Look at all these things. Yeah, I'm fancy. If you go to community, you can click on here. It will take you to our threads, all of our threads, and it looks a little overwhelming. But what you can do is click over here and scroll down to the practice prompts section. You click on that. For my class, you go scroll down to AP Chemistry. But if you're taking any other classes, you can answer and work on those there. So I scroll down, I hit AP Chem, and I've listed a problem from Unit 1, Unit 2, Unit 3, and Unit 5. So you can try those out there. I plan on doing a couple more there, okay? Awesome. So that hopefully is helpful. Is there any thermochemistry or thermodynamics questions that you guys have that you want me to ask before I head out today? Speaking of thermodynamics, I'm warm. I'm wearing a sweater. I don't know why. Awesome. So don't forget next Tuesday. Yeah, for sure. Don't forget next Tuesday, we are going to be doing our last unit. It's going to be equilibrium. On Thursday, a week from today, we're going to be doing some practice questions as a group. And then on the 13th, the day before the AP test, we're going to have pretty much an entire afternoon of streaming. You guys got this. I am so impressed with the questions you guys are asking, and you'll be wonderful. What are the classes on the Fiveable website? Let's see. I'm wondering. Classes. I don't see a classes tab. Yeah. So if you have to head out to another CRAM session, kick butt. I will see you guys in a couple days. Perla, I'm trying to find the classes thing that you're referring to, but I don't see anything that's labeled classes. I'm on my page at least. Okay, so under the community, all categories. Oh, does your teacher do Fiveable? Like, does your teacher subscribe to the Fiveable website? Yeah, so it's your specific like at school class. Yeah. All right, right on, guys. Have a good one. It's super great seeing all you guys. I'll see you next week for Equilibrium.